Okay, ladies and gentlemen, so today we are going to be talking about the inverse of a square matrix. So before we can talk about what this is, what is a square matrix?
Same number of rows.
Very good. It's the same number of rows as it is columns. So are both of these matrices here square, A and B? They sure are, right? Because matrix A has what order? 2 by 2. Matrix B has what order? 2 by 2. Very good. Okay, so I would like you right now to determine what A times B is in your table groups. That's what I'd like you to do right now. Okay, Ryan, what did you get for when you multiplied A times B? What did you get, buddy?
I got
1, 0, 0, 1. Can someone else verify that? 1, 0, 0, 1? Let the record show 2 or 3 people can also verify that. Good. In your table groups then, also now please determine B times A. Are they necessarily going to be the same thing? No, because in our previous lesson we learned that multiplication with matrices is not commutative, meaning that, like in normal multiplication, 7 times 3 is the same thing as 3 times 7. That's not necessarily the case for matrices, though. But in this case, I'd like you to figure out what is B times A. Theo, what did you get for when you did B times A? What did you get?
1, 0, 0, 1.
1, 0, 0, 1 again, right? Interesting, okay? So this matrix, you guys, ladies and gentlemen, this has a very special matrix. This is called the identity matrix. And for shorthand, sometimes we write it as I subscript n, identity matrix of your n by n matrix. So the reason it's the identity matrix is because it's the matrix you can multiply and you receive back, get the identity. 1, 0, 0, 1. Kind of like when we did inverses, right? To show that two functions were inverses of each other, you would plug one into the other and you get out the identity x back, right? Same kind of concept here for matrices, okay? So there's something that's special about these two things, right? So here's what it says. Now that we've accomplished what we came to do with multiplying those two things, and we notice that we get 1, 0, 0, 1, a 2 by 2 in either case, here's what we can say. So, we can say that if A times B is equal to our identity matrix, which is the same thing as B times A because we know matrix multiplication is not necessarily commutative, right? If we can say this statement, then here's what we can say. We can say that B is what's known as the inverse of matrix A. So it turns out that matrix B, up here, this matrix, I'll make this a little smaller so you can see. Matrix B is what's called the inverse to matrix A. And this is kind of what we're noticing here. So I'm going to sum it up for us in the next one. So I'll give you the formal definition of what an inverse is. So this will be the second idea. Okay? It is the formal definition. Okay? And the way that I break this up is I break it up into 3 parts. I go part 1, part 2, and part 3 for the formal definition for the inverse of a square matrix. So here's the setup part. So number 1, we're going to say let matrix A be an n by n matrix. Okay, so A is an n by n, which means it's a square matrix because it's n by n, rows and columns match up. And we're going to let I sub n be the n by n identity matrix. Okay, so that's our setup. So A is some square n by n matrix. I sub n is some identity square matrix, right? And so then part 2 is going to be this. Say if there exists a matrix, and we'll call it A inverse, A negative 1, the inverse matrix, representative inverse matrix, such that A times A inverse equals our identity matrix, which is the same thing as A inverse times A. If you can say all of that, then part 3, A inverse is called the inverse of A. Okay, so a couple of key parts here. This thing right here, this is how we're going to represent A inverse, and this statement right here is pretty important. So it says that if there is some matrix out there that when you multiply A times A inverse, you get the identity, then that A inverse is defined as the inverse. So as an example, if we go back to this one here, and I'll come back to it in just a second.
Do you just have to do
Okay.
both?
Yeah, I gotta do both.
That it's the identity.
Yeah. So in this case, B was the representative of A inverse in the actual formal definition, right? This one right here, B, is representative of the A inverse in this. So the formal definition, this part right here, our example was that B matrix. So now that we kind of talked about the 3 conditions of what an inverse actually is, namely A times A inverse is identity, the question becomes then, how do you find it, right? So there's 3 parts to consider for this one too. This lesson has a bunch of 3 parts. Okay, before we can talk about whether or not how we find it, the how part, we've got to talk about the specifics. So first one here says this, right? You have to realize that not all square matrices have inverses. So just like with regular functions, right? Not all functions have inverses. Same thing with matrices. Not all matrices have inverses. Okay, so that's the first thing you have to keep into consideration. Second thing you have to keep into consideration is this. If they do, okay, so if they do, then we call that matrix invertible. So we have a vocab word here. So let's get some definitions down. So if our matrix does have an inverse, and not all of them do, if it does, it's called an invertible matrix. Well, then you're probably asking, what if it doesn't? So if not, then we call that a singular matrix. Do you guys remember the Singular Wireless Company? Yeah. What happened to them? Invertible and then singular, right?
AT&T.
Yeah, AT&T, right? So not all square matrices have inverses. If they do, they're called invertible. If they don't, they're called singular. And then the third idea here is if A inverse exists, then it is unique. So we're getting into some heavy sort of math theory here with all these words. So invertible, singular, and unique. So what do you think the word unique means if it does exist?
It's rare.
Rare, that's good. Okay. What else do you think it means?
It's rare.
It's one of a kind, meaning that there's only one. So if a matrix does have an inverse, then it only has one, and we're going to learn how to find it, okay? Only one of them exists. It's not a multiple answers. All right, now that we've talked about those 3 components of inverse for matrices, we're going to actually find one if it exists, all right? So here's how we're going to do it. Here's the first strategy. We're going to actually, since the identity matrix has something to do with it, I'm going to write down the identity matrix right next to it, 1, 0, 0, 1.
So that's always the identity matrix.
Yep, the identity matrix is 1, 0, 0, 1. That is the representation for the Gauss, right? If you put something in reduced row echelon form through Gauss-Jordan elimination, we get this, right? So the goal here for us, ladies and gentlemen, the goal is to reverse these here. The goal is this, right? Right now I have matrix A right here, and I have the identity matrix here. Is that true?
Yes.
Okay. The goal is to get this, the identity matrix here, and the leftover part will be A inverse. Crazy, huh? We're going to reverse these. Okay?
What's the letter next to the I?
It's N. It's N, just like it was up here. It's the same thing, right? Just like it was right there, just like it was right there, right? Oh, that's what that means. Okay? Same thing. So here's what we have. I have matrix A, and then I have the inverse. The identity matrix. I'm going to switch these around to have the identity matrix here, 1, 0, 0, 1, and the leftover part, the leftover matrix, will be my inverse. So let's go ahead and do all of that. So I'm going to write this out as 1, 4, 1, 0, negative 1, negative 3, 0, and then 1. Okay, so the goal is to get the left-hand side to be the identity matrix, and the right-hand side will be A inverse. Okay, so far so good. I have a 1 right where I'm supposed to have a 1, right? But I want a 0 below that. So what should be my first move, guys? Yeah, that's a good call. Let's do row 1 plus row 2 and put it there. Okay, so if I add this, I'm going to get 1, 4, 1, 0. If I add these together, I get 0, 1, 1, 1. All right, we're almost there, huh?
Yes.
What's our next move going to be?
Negative 4 row 2 plus row 1.
Negative 4 times row 2 plus row 1. Awesome. Okay. So that's going to give me 1, 0. What do I get here? I get negative 4 times 1 is a negative 4. Negative 3, very good. Negative 4 times 1
Negative 4.
plus 0.
Negative 4.
Good, and then the bottom stays the same, right? 0, 1, 1, and 1. So check it out. Now I have the identity matrix, don't I? So what must this be?
The inverse.
The inverse. So therefore, A inverse is equal to negative 3, negative 4, 1, and 1. Not so bad, right? Okay, we're going to do some checking here. If indeed this is true, then we should know this. We should know that A times A inverse should give us our identity IN, right? And that should be the same thing as A inverse times A. We're going to use our calculators for this, okay? So A,
Go back up.
yeah, I'll go back up here. I'll string it down for you. The original matrix A was 1, 4, negative 1, and negative 3. And our inverse matrix that we just found was this. Negative 3, negative 4, 1, and 1. We're going to multiply those together, and hopefully we should get 1, 0, 0, 1. That's what we should get. So let's do that right now in our calculator. So take your calculator out. Save us a little bit of time. Okay, I'll write this down here. Okay, I'm going to enter this into my calculator. So turn on, go to second matrix, go to edit, enter. We're going to do a 2 by 2. So I'll do 1, enter, 4, enter, negative 1, enter, negative 3, enter. Sweet. Second quit. Go to a matrix. Go to matrix B. Enter that one. That's another 2 by 2. Right? So I'll enter in a negative 3, a negative 4, a 1, and a 1. And then I'll do second matrix 1 times second matrix 2. And if I multiply these together, oh
I
shoot.
think you put in a 6.
Did I put in a 6?
6B
Yeah, I got 1, 0.
Did you guys get it all okay?
Yeah,
So is it the second one here?
I believe so.
Yeah, there it is right there, huh? That should be a negative 3. There we go. All right, so second entry. There we go. Now I got it back.
Yay.
There is another way to do this. Another way to find the inverse. Check this out. Second matrix, I can go A. Second matrix A, so enter. And then see this button right here? Inverse. Boom. Enter. Hey, is that the same thing that we got over here?
Yeah.
Check it out. Negative 3, negative 4, 1, 1. Yes, it is. Okay, we got it, right? Okay, I gave you matrix 2 by 2. 1, negative 2, 2, negative 3. I want you to find A inverse using the identity matrix. You can check it on the calculator, but you have to have the process down and the mathematics behind finding the identity matrix. Using the identity matrix to find the inverse. All All right, Bobby, go ahead. Lead us through. What did you do?
So
Everybody else pay attention, those of you, because not everybody said they got the same answer as we did. So, Bob, what'd you do?
first I did -2 row 1 plus row 2.
Negative 2 times row 1 plus row 2. Yep, I forget that. So then that gave you a 1, -2, 1, 0. Then what?
0, 1, -2, 1.
Okay, good. Then what'd you do?
I did 2 times row 2 plus row 1.
2 times row 2 plus row 1, and that gave you what?
1, 0,
Yep.
-3, 2.
Mm-hmm.
0, 1, -2, 1.
-2, 1. Okay, so it turns out then A inverse was -3, 2, -2, and 1. Is that true?
Yep.
All right, good. Now, everybody, I want you to take a look at this matrix here, and then I want you to take a look at this matrix here. Do they look similar to you guys, or do you guys notice anything? What do you notice? Ryan, what do you notice, buddy? What?
They're flipped diagonal.
They're flipped diagonal. What do you mean by that?
Like it's flipped vertically and then flipped horizontally.
Flipped vertically and flipped horizontally, huh?
But the one above
Huh.
that isn't.
Okay, so you say flipped horizontally and then flipped vertically, right? So then let's go back to this one up here, right? We had these two matrices right here. Is it the same thing for this one? Are they flipped horizontally and flipped vertically?
No.
What do you think, Theo?
Well, with all the ones we've seen, A11 and A22 are switched, and then A21 and A12 are multiplied by -1.
Very, very good. Okay, so here's what he's saying, right? Here's basically what he's saying. You guys are almost on our track. So it looks like these two, how are these two related?
They're switched.
Those two switch places, and these two switch what? They switch signs. Okay. So notice I make like a parenthesis, like a percent sign, right? Right. Although it's like a backwards percent sign, right? Okay. So check this out. Same idea, right? Looks like these two switched places. Is that true? Those switched places, and these switched signs, right? That's only half the story. You are totally right. It's only half the story. So that leads me to there is a formula for finding A inverse of any 2 by 2. This only works for 2 by 2s in this case. Okay. For 3 by 3s and higher, we're going to use Gauss-Jordan elimination and our calculator. But for a 2 by 2, here's what you get. So let's say you're given this. A is equal to some matrix. I'll call it little a, little b, little c, and little d. Okay? Okay? So here's some 2 by 2 matrix. First things first, number 1, if A times D, so if this product here, that diagonal, minus B times C, so this diagonal, as long as that is not equal to 0, then A is invertible. And what does the word invertible mean, you guys? That means it has an inverse, right? Okay. So number 1, check to see if the cross is not equal to 0, then A is invertible. Then number 2, the formula goes this. A inverse is going to be 1 over your product there. A times D minus B times C, multiplied by the scalar that we just noticed. A and D switch places. Okay? So this is a D. This is your A. And then B and C switch signs. Negative B, negative C. So this is super important, but it only works for 2 by 2s. And it only works if AB minus BC is not equal to 0.
Is the matrix and that little thing equal to each other?
Okay, so while everyone's copying that down, since we only have a little bit of time left, let's say we have this 2 by 2 matrix. A is 3, negative 1, negative 2, 2. So the first thing I'm going to check is this. I'm going to do 3 times 2 and subtract off a negative 2 times a negative 1. That gives me 6 plus what? Or, sorry. This is going to be 6 minus, so what? A positive 2?
Negative 14.
Whoa, negative 14. What?
Wait.
I'm getting 6 minus 2. I'm getting 4 out of this thing. Are you guys getting 4 out of this thing? Okay, I'm getting 4, right?
Okay. Well, that is a negative 1.
Okay, sorry. So 6 minus and then 2 is 4. I'm getting 4, yeah?
Wait, what? Wait, 4?
Yeah, no, not 14, 4. Okay, good. So 4 is not equal to 0. Is that true?
Yeah.
So is this invertible or not?
Yes.
Yes, it is. Therefore, A inverse is going to be 1/4 times, okay, now, these two switch places. So 2 goes there, 3 goes there. These two switch what?
Places.
Signs. So 2 and 1. So therefore, A inverse has to be 1/2, 1/4, 1/2, and 3/4. That was a lot faster, huh? What do you guys think?
Yeah.
Is that true? A lot faster?
It probably would have been a lot worse to try to do that.
Probably would have been a lot worse to try and do it the other way, right? Okay.
With fraction density.
Let's do example B. Will. Okay, here's example B. Let me give you this matrix. A is equal to, how about this one here? Let's do 3, negative 1, negative 6, and 2. Okay, let's multiply. We're going to do 3 times 2 minus negative 6 times a negative 1. That's 6 minus 6. That gives me what? 0. So therefore, this matrix is singular.
I am not with it today.
That matrix is